So today is lecture number 8, and we're going to have 2 lectures on an introduction to game theory. And whether or not game theory is lumped into, the subtopic or as a subtopic of artificial intelligence, it's definitely not. But I think that you can use game theory to help yourself understand some of the algorithms that we will be learning, which are definitely covered under AI. So whether or not something is AI, nowadays everything is AI. But I think game theory, which does come from the field of economics originally, is very interesting. So we'll wait for a couple of people to come in. Are there any spare pieces of paper out there? All right, someone in the back, or hand these back to people who don't have a piece of paper yet. And here, for the people just showing up, is what the paper means. We're going to be playing a game. And you're not supposed to talk to people about your number, by the way. This is supposed to be secret. So the game is called Choosing Numbers. Very fancy name for a game. Everyone is going to secretly choose on their piece of paper a number between 1 and 100 inclusive. We will calculate the average number chosen, so I'll add them all up and divide them by the number chosen, and then the winner, who will get a 1% bonus on the midterm, will be the person who is closest to 2/3 of the average number that was chosen. So I'll give you 30 seconds or a minute to answer that, and if you have already answered, please just come up, or maybe give them to someone and then they'll come up here and just put them on the table. You're being volunteered to put them up, I think. I guess write your initial or something too. Well, you can tell me who it was. I'll trust you. Yeah, just put them there. Yeah. Well, I trust no one would claim to have the number if they didn't write it. But so what I'm going to do while this is happening is I'm going to start entering them. So if you could lay them up here so I can... Yeah, that's fine. Thank you. I'm going to start entering them into this spreadsheet. Yeah, just lay them there and I'll get them. Thank you. Thank you. You don't need to fold them 10 times. Just lay it there, it's fine, thank you. So this is what you get when you come to class. You get to play games. Just lay them down, thanks. I think I've gotten more pieces of paper than people in the room. Everyone pass one in? Okay, if not, too late. Okay, so the average, 47. That's crazy. That's the highest average I've ever seen. And this is 2/3 times that. Let me just make sure I did that correctly. Equals average of this to that. Yes, okay. So who's closest to 31? We got a 28. Oh, there's two 32s. Okay, so hand up if you were one of the 32s. Okay, so we got two 32s. Why did you choose 32?
Because the average value is 50 and the
How do you know the average value is 50?
because it's 1 to 100.
Oh, so the average of the selectable range. Okay. Who chose 5? Okay, why did you choose 5?
I didn't understand the game. It's
Okay.
Sorry.
Who chose... Okay, you don't have to raise your hand if you don't want to. Who chose 91? What was the reasoning for that? Just your favorite number?
Yeah.
Okay, cool. Now, I'm going to kind of leave that to marinate for a little bit, and then in the next lecture, we're going to play it again, and we're going to talk about it a bit more and see why, right? Because one of the things about game theory is that you go through life and no one has ever talked about how to make decisions. And this is like a decision, right? You make a lot of decisions in life. This is one of them. This is a bit of a weird one. Now this is mathematical, but it goes to show that decision making in a group of people matters. It depends on a lot of factors. You know, the time we play it right now, if we play it again, there'll probably be a different answer, which is dependent on the previous time that we played it. Right, and all sorts of stuff. So we'll get back into this as time goes on, but let's finish this lecture, and then that's sort of a teaser for the next lecture, I guess. Okay, so we just played the numbers game. So what is game theory? So game theory is sort of a mathematical models for decision making, and decision making is something we do all the time, and you're just kind of maybe given a goal, stay away from that area, that's not a good area, or try and make money, or try and find someone who cares about you. But how do we make those decisions? Well, there's certainly no handbook for life, but game theory can be used, not necessarily to make those type of decisions, but to make other types of decisions which are very important. And so game theory is basically an analysis of strategic actions in scenarios which can be defined as games. And I don't mean game like it has to be checkers or chess, but anything in which you can define, has these properties, which we'll get to in a bit, which is a lot of different scenarios in life. And this has many, many different uses in social science, computer science, economics, and really everyday life, in my opinion. And nobody really teaches us how to make decisions, so let's, at the very least, look at the mathematics of some ways that we could make decisions. And the way we're going to do that is we just played one game, now we're going to play a different game. And these are theoretical games. Any of the numbers that I put into these games are just kind of made up. They have some intuitive sense, but they're not exact. They're just examples of games. So here's another game. 2 players secretly and simultaneously make a choice with a defined outcome. And the choices here are either going to be you're going to choose alpha or you're going to choose beta. Those choices of alpha or beta have nothing to do with the letters. They have no real-world examples. It doesn't mean left or right or up or down or black or white or whatever. It's just some symbol that I'm putting on you made one choice or the other choice. Just something to differentiate them. Now here's the outcomes in this game. If you choose alpha and they choose alpha, you get a B-. If you choose alpha and they choose beta, you get an A. If you choose beta and they choose alpha, you get a C. If you choose beta and they choose beta, you get a B+. So, look at that for a second and just put a hand up. There are literally no wrong answers to this, and we'll see why in a bit. There's no right answer and there's no wrong answer. Put your hand up if you would like to explain to me what you would choose and why. Because there's a lot of different ways that you could make this decision. And it's very interesting how you would make this decision before and maybe after you've been taught a little bit of basic game theory. Yep? Okay, so these are not 4 different choices. There's 2 choices. So would you choose alpha or beta?
I'll choose the decisions that would result in the last, the B+. So I'll choose beta.
So you can't choose B+, right? Because that depends on their choice.
Yes.
So, but you would still choose beta. So why would you choose beta?
I guess just guaranteed. It's okay. So I guess So does this also affect what they get? I guess.
No, this is what you get, and then if they're playing the game, they get the opposite thing.
The opposite.
Yeah.
So I guess I would choose something that would guarantee at least like both of us get. Well, most likely both of us would get a B plus.
So you're valuing what you would both get,
Yes.
putting some value on that. Okay.
Kind of like the prisoners, I guess.
Yeah, we'll get to that in a second. Anyone else that would have a different choice? Would anyone choose alpha? Okay, why would you choose alpha?
Because I'm guaranteed to like get a good grade.
Okay, well, within the definition of good grade, but you're looking at sort of the maximum possible thing that you could get.
Yeah,
Okay. Okay, and if you're saying at least a good grade, maybe also like looking at the average or something like that. So there's lots of different ways that you could look at this problem, and half the class would probably choose one, and half the class would probably choose the other. So what we're going to do is let's first put this game into a form that's a little bit easier to parse. And I recommend doing this anytime you have a real decision to make, because this is a whole lot of word soup, and it's difficult to really make sense of it all at a glance, because you're reading sentences, you're trying to parse information. By the time you've read the last thing, you've forgotten what the first thing was, right? And this actually does matter in decision making. So what we're going to do is we're going to take this and we're going to put this into a matrix. Here's that matrix, okay? So here's me, and here's the other person. I'm just going to call that the partner for now. And here are the outcomes. And this is called an outcome matrix because we've just put it into a matrix. So we've taken that same game, and if I choose alpha and they choose alpha, I get a B minus. If I choose alpha and they choose beta, I get an A. If I choose beta and they choose alpha, I get a C. And if I choose beta and they choose beta, I get a B plus. Okay? So that is, like, in my opinion, a much, much easier way to parse the outcomes of this game. And you can see them all at a glance rather than having to sort of read all these sentences and try and keep all that information in your head. And if we flip it, because if the other person is also playing this game, this would be the game of the grades that the partner gets, right? So if we both choose the same thing, then they would get the same thing. But this is like a symmetric game where if I get something and they get the other thing, well, if we flip it, then it's just flipping that diagonal, right? So here where I would get the C, they get the A, and where I would get the A, they would get the C, okay? So this is two matrices, and it's still a bit hard to look at. So what we're going to do is we're going to combine these into a single matrix to make it the easiest possible way that we could look at that. And so what this final outcome matrix, this sort of determines the outcome of the game. So again, if I choose alpha and they choose alpha, we would both get a B minus. If I choose alpha and they choose beta, I would get an A, so this is the left player over here, and they would get a C, that's the top player over here. If I choose beta, I would get a C, or if I choose beta and they chose alpha, I would get a C and they would choose an A. If we both choose beta, then I would get a B plus and they would get a B plus. So this is the outcome matrix for this game. And even though it's not like a game like you would think Snakes and Ladders or Tic-Tac-Toe or something like that, it is a game, right? We have some sort of outcomes that are happening. So in this game, we have actions, strategies, and outcomes. But it's not yet a fully defined game. What might we be missing? Put a hand up. I can't see. Yep. So there's no real probabilities in this game because it's a defined deterministic outcome. But there is something that's kind of missing. And we kind of saw that, like, when we were trying to see what would someone choose, someone was valuing one thing and another person was valuing another thing. So then what might we be missing from an actual game that we could apply an algorithm to here? Just I gotta have a hand up. Yep.
Some kind of value function for each agent.
Sure.
See what they value.
Exactly. So the outcome here is like the grades, but what we actually want is called a payoff, like a numerical value. And so what is our objective or our goal in this game? And so we have outcomes in a particular environment, and we're going to associate payoffs with those. And the thing is, game theory is not going to help you take outcomes and translate them into payoffs. Like, that's something that you kind of have to do. Like, if you're doing, I don't know, some auction of a big asset at a company, like whether or not you get that asset and how many dollars it is. Maybe you translate, having this into so many dollars, or maybe some people might lose their jobs, and so that's some negative value or whatever. And so whatever the outcome is, you have to translate that into like a numerical payoff, so then you can apply an algorithm. And game theory does not help you with that part, but once you do have the payoffs, the numerical payoffs, it can help you algorithmically with how to make the decision. So if you have payoffs, then game theory can help you achieve them. So for example, maybe we care, I want to choose the option that would have the best possible outcome for me. That's all I care about, right? Or maybe I want to take the average of what I would get and the other player would get, or something like that. So these are things you'd have to take into consideration when taking the outcomes and translating into payoffs. So let's just do an example here. Let's assign a numerical value to an outcome, and essentially this is going to be how much do I like that outcome. And the more that I desire that outcome, the higher the payoff is going to be, right? So if I desire it more for whatever reason, that number is just going to be higher. So I'm going to assign completely arbitrary yet somewhat intuitive numbers to this grades game. So imagine one of the players is greedy and just assigns higher payoffs if they do better than the partner. That's all we're going to think about. So let's say that like a B- is kind of a neutral grade, not great, not terrible. But if I get an A, that's a 3 for me. I don't care that you get a C. I don't care that you get an F. All I care about is my grade. So if we translate those outcomes over here into some numerical values, this might be what we get over here. Okay? So these numbers are also what's called utility. So these payoffs are called utility, and it's called utility because it's how much I value that thing. If I place a higher utility on something, I want it more, right? And again, coming up with these numbers is not necessarily a trivial process. If you're playing a game like chess and you want to describe it in these sort of terms, well, then maybe it's easy. 1 for a win, -1 for a loss, 0 for a draw, something like that. But if you're trying to make like a harder decision that has some like, oh, maybe this person is going to be punished for something, how do you assign numerical values to that? It may be more difficult. So these numbers are utility, and the whole point here is that since you have spent some time assigning this utility into numerical form, then your only remaining objective is now to maximize that utility, right? So I want to get the highest number for me, and that's not being necessarily greedy because I have put all of my self, like what I care about, into those numbers. So a higher number doesn't necessarily mean only I benefit. It could mean that we both benefit, or that my child benefits, or something like that. But I've already done that translation, okay? So in this example, if I get a B- and you get a B-, that I'm going to say that's a 0, because B- is kind of a neutral grade. If I get an A and you get a C, well, that's great for me. I'm going to assign that a 3, because I only care about myself in this particular situation. So now that we've translated it like this, what should you do, right? So again, please stop shouting. Hand up if you would now tell me, someone different, what you might do in this situation. Again, there's no wrong answer yet. Yep.
I would go for beta because in both cases I have a 25% chance of getting a -1, but then with beta I have like a 35% chance of getting a positive number.
Okay, so you're talking about like probabilities, and that would be something if you assumed, for example, that they're going to choose something at random, right? Because otherwise probabilities don't make sense. So that's a good way of looking at it. Like if the other person just randomly chose something, what would be the highest probability of me getting something? Anyone else? Yep.
I would go for alpha because higher risk, higher payoff. Plus, if people start thinking like this, probability they start choosing beta, then it's good for me.
Okay, so just to repeat, someone is alpha you wanted to choose, right? So alpha because it's sort of a risk versus reward analysis, and if you think someone else is going to choose beta, whatever. Okay, so let's have a look at this algorithmically and see what we would do. The key here is to consider all the possible choices. So even though this is not a traditional search algorithm, there is a little bit of search in here, insofar that we are going to consider everything that could possibly happen, and then see what would be the outcome for that. So what we're going to do is, I'm me over here, and I'm going to see what I'm going to do. Well, instead of just looking at what I can do and their outcomes, let's first see what the partner could do. Okay? So first, let's consider what would happen if the partner chose alpha. So if they choose alpha, if I choose alpha, I get a 0. If I choose beta, I get a -1. Right? Okay. If they choose beta, if I choose alpha, I get a 3. If I choose beta, I get a 1. So alpha is just always the best choice. Right? So no matter what the other person does, if I choose alpha, I do better, strictly better, than if I had chosen beta. So all these intuitive notions that we may have been using 2 minutes ago to make our decisions in life, if we see what the other person, all of their possible things, and if one thing is always better for us to do, well, you'd pretty much have to do that thing, right? Because no matter what the other person does, it's always better for me. And this isn't some sort of situation where you're being tricky. It's like, yeah, but if I did the opposite of this, no, you'd still do worse, right? So there are cases in which we analyze everything that the other player could do, and if in every single situation of what they could do, one of my choices is better, I should probably take that choice. So this is called strategy domination. Very important concept in game theory. And we say that a strategy alpha strictly dominates a strategy beta if my payoff from alpha is strictly greater than that of beta, no matter what the other players do. Okay? Now, do not play a strictly dominated strategy. So if beta is strictly dominated, don't play it. Why? Because alpha will always do better than it. Okay? And the strategy that dominates it is better in every possible case. Now, just a quick note before we keep going. Alpha is always better than beta. So when we talk about domination, it's easy to think of it from the point of view of the thing that's better. So we're not calling alpha a dominant strategy. We are saying that beta is a dominated strategy because something is always better than it. And we'll get a better view for what I mean by that towards the end of the lecture. But we're trying to say, when I say, is there a dominated strategy? It doesn't mean, is there a single best strategy? It means that, is there something that something else always does better than it? And if that's the case, well, then you should choose that thing and not the thing that always does worse. Sorry, I got something in my eye. Okay. Someone before mentioned the prisoner's dilemma. And the prisoner's dilemma is another game. Who has heard of the prisoner's dilemma before? So it's a very popular problem in computer science and mathematics. Here's the problem. 2 prisoners in separate cells. So the police have arrested 2 people. They put them in separate cells so that they cannot communicate whatsoever. Right? You've got to divide and conquer. You can't let them talk and get their stories straight. You've got to question them individually. The guards asks each of the prisoners to rat out the other player. And rat out means to tell on them, to snitch, right? To say, admit that you did it. Say that they did it. Something. Give us the evidence that we need to lock you up. And here's the outcome of this game. Even though this is a very serious situation, we can still phrase it as a game. If neither of them tell on each other, and now this is not a true representation of the justice system, okay? I'm not saying that this is how criminals think or how judges think or anything like that. This is an arbitrary assigning of numerical values to a situation. So if neither of them tell on each other, well, what happens? That's kind of annoying for the cops, right? They've got enough evidence to kind of put them away, but not the confession. So they're both going to go to jail for a year if both of them keep their mouths shut. Okay. If both of them tell on each other, then they got the evidence that they needed, but the cops are like, okay, at least they confessed. But they have stronger evidence, right? So they're both going to jail to 2 years. All right, so that's what's going to happen. And again, this is not necessarily what happens in real life. It's just made up numbers. If one of them tells and the other person doesn't, then the cops are like, okay, they told on that person did it, we can put them away for a long time. So the teller goes free, and the other goes to jail for 5 years, right? That's how it works. So I didn't do it, they did it. And so that's what's going to happen. So, and if they both tell on each other, then the cops are like, they're both guilty, so they'll go for 2 years. So that's it. Both go to jail for a year. If neither tells on each other, if they both tell, both go to jail for 2 years. If one person rats out the other person, the teller goes free and the other goes to jail for 5 years. So that's a bit hard to parse. Let's put it into a matrix form. And I am going to assign, now again, these values, this utility, this payoff, is difficult to come up with, right? You may have a different utility for if that other person is your friend or your enemy or your mother or, you know, a random person that you've never met before who you just decided to commit a crime with. Maybe you were just a passerby and they arrested you as well, right? So what I'm going to do is just assign -1 to every year that you're in jail. But maybe, you know, going to jail for 2 years isn't necessarily half as bad as going to jail for 4 years, right? Like, not going to jail at all would be amazing. So, but this is just the utility that I'm assigning it. But just keep in mind that game theory can't help you assign these values. You have to do that for yourself, and then game theory can help you solve it. So, if prisoner 2 tells, right? Oh, so the thing is here, what are we going to do? Right? What are you going to do in that situation? So, we've made up our mind on our payoffs here, and we're going to do the analysis. And I'm prisoner number 1, so what I'm going to do is look at everything that prisoner number 2 could do. So if prisoner number 2 tells, so we're going to be looking at this column, if player 1, if they tell, they get -2. If they stay silent, they get -5. Right? And if player number 2 stays silent, if player number 1 tells, they get 0. And player number 1 stays silent, they get -1. So, ratting out the other person strictly dominates not ratting them out in this situation. So that's kind of the gist of the prisoner's dilemma, is that in this case, now I'm not always saying that like snitching on somebody is always better, telling the truth is always better, whatever. I'm not getting into that morally or philosophically. Just that in this form of the prisoner's dilemma, the outcome is that it's just better to tell. Because no matter what the other person does, you're going to have a better outcome. There's no trickery to it. Look, I'm going to either get -2 or -5, or 0 or -1. And so it's -2 or 0 versus -5 or -1. So telling is always better in this case. Let me just take a sip here. Now, there was this game show that was on for like half a season or something. I think the actual name of the game show was called Golden Balls, because you got these little golden balls, but the game show was basically the prisoner's dilemma, okay? So 2 contestants, they had 2 balls in front of them, and they secretly chose to simultaneously reveal, split, or steal. And so if they both split, they both get half the money. So let's say it's $100,000, right? If they both choose split, they each leave with $50,000. If they both steal, they both get nothing. If one splits and one steals, the stealer gets it all, okay? And this is essentially a form of the prisoner's dilemma, right? It's not exactly the same, but it's close enough. And the idea here, the drama of the show, how do you take this and stretch it out into 22 minutes, 8 minutes of commercials, right, which is what they're trying to do, is they let them talk for like 15 minutes about it. And the point is, the host of the show makes it very clear that nothing that happens during that conversation is legally binding. They can shake hands, they can sign a document, they can talk and say, oh, I'll do this, I'll do that. Oh, I promise if you split, I'll split. Nothing is legally binding. It's just a whole thing of trickery, right? So, what happens in this particular episode? This guy basically falls in love with this woman, right? Sitting across from her. She's sweet-talking him. Oh, I have a grandmother in hospital. I have 3 kids. I have all these debts. But $50,000 would pay for everything. So I'm just going to split. So split with me. We'll go our merry ways. We'll both have $50,000. It'll be a beautiful love story, right? Of course she steals. And he splits. And she gets everything. And he walks away very, very sad. And so that was the name of the game, right? To introduce some sort of human drama into this show. So let's look at the game from a game theoretic point of view, right? Because our goal as algorithm people is to take the fun out of life and just algorithmically solve all the problems, right? So let's look over here. If the other player, again, what do we want to do in this situation? If the other player chooses split, then I get a half. If I choose split, I get 1 if I choose steal. So steal is better. If the other player chooses steal, if I choose split, I get 0. If I choose steal, I get 0. Okay? So stealing weakly dominates splitting. Weak domination means that I do at least as well in all of them, but I do better in at least one of them. Okay? So the game creates drama by allowing players to talk and make a deal and all sorts of stuff here. But the idea of this was to introduce this concept of weak domination. Here I managed to find this YouTube clip, and this was my favorite episode ever because I think this episode kind of stopped the show. They realized how stupid the show was after this. This guy over here on the right, after the host sits here and talks for a few minutes to introduce the game rules, and then this guy goes, whatever the other guy's name is, he says, hey, here's what's going to happen. There's a 100% chance that I'm going to steal. So you can either choose to steal, and we'll both get nothing, and I'm fine with that. I have a pretty comfortable life. Or if you choose split, I'll get all the money, but I promise I'll give you half of it. So you are either going to walk away with nothing or hope that I give you half the money. Right? And this guy is like, wait a minute, let's talk about this. Like, we'll do this and we'll do this. And my dad used to say, and the guy's like, that's cool. I'm choosing steal. So you make up your mind, right? And in the end, well, you can see, I guess I'll spoil it for you. This guy's like, well, what am I going to do? Right? And so the other guy chooses split. Otherwise, he's taking nothing home. And in the end, this guy actually chose split. And so it was like this sort of heartwarming thing. But I think after that, they realized how stupid the show was, because game theory shows, just say you're going to steal, because it's weakly dominating the other thing. So anyway, the YouTube video is there. It's like 5 minutes. It's pretty entertaining. But an important note here is that the decision-making using the game theory assumes that the payoff matrix is accurate for your utility, right? So over here, when I made this matrix, I gave half the value of splitting because you get half the money. But I don't think anyone would realistically, right now in your life, I was a grad student for nearly 10 years, right? I understand what being a grad student is. Having $50,000 is probably way better than half of having $100,000, right? Because it would just make that difference in your life. So having $100,000 is obviously better, but it's probably not 2 times better than having 50 grand, right? At least that's how I felt in grad school, because 50 grand I could just buy my apartment or whatever and I'd be done with it. That was a long time ago when 50 grand might buy you. Yeah. Not a house, but anyway, what I'm saying is you might say that you getting 50 grand is actually 0.7 or something like that. Or you might say that if the other person walks away with nothing, I feel bad. So you might not have these exact things. These are, what we're doing here is translating the game into a get more money, very greedy type of game. And that might not be your outcome. That might not be your utility. So just make sure that you realize that me saying stealing is probably the way to go has to do with the assignment of these utilities, not necessarily your utilities. Okay. And you might not care as much about beating the opponent or getting a higher payoff. And so the sort of other lesson here is that direct translation from real-life prizes into this payoff matrix may be difficult. Okay. We looked at the grades game. And these were the grades that are obtained by players in the grades game, right? So we showed the example where someone who was just strictly greedy and said, I'm going to assign utility to these grades based on me getting a higher grade means higher number, that's it. But what if we had some different players? So in the previous playoff, payoffs, we had greedy players. And in the new payoff, let's say that we introduce some sort of what I'm going to call a caring player, right? Which factors the other person's grade into it somehow. Maybe you have a friend that you're in the class with, and you want them to get a good mark too. So maybe if I got an A and they got a C, that was a 3 because I just really want the A. The fact that they get a C didn't matter to me. But now maybe a caring player, I care that the other person got a C. That's like a -1 to me, right? And maybe CA was -1 because I was just getting a C, but now I'm hurt that the other person gave me a C and they got an A, right? So this person maybe is a little bit more emotional or something like that. So I'm angry that I got less than they got, right? This is maybe more of a human type game. So here's what we would get in that case. So in this example, both the players are greedy and assign higher payoff to their own grade. And sorry, this is still the greedy one. And they don't factor what happens to the other player in at all. But if we had different payoffs, right? So maybe we have a -1 now instead of a 3 because maybe there was some guilt associated with the other player getting a lower grade. Maybe my -1 is now a -3 because I'm like angry about that. So let's look. Is there a dominated strategy in this particular case? So let's have a look at it. If my partner were to choose alpha, if I choose alpha, I get 0, beta gives me -3, so alpha is better. If they choose beta, alpha gives me -1, and beta gives me 1. Okay? So in this case, there is no dominated strategy, right? So if you want to decide how you're going to choose in this case, first, see if there's a dominated strategy. If there is one, don't pick it. If there is one that dominates everything else, pick that one. But if not, now you may have to resort to the things we were talking about before, right? Where, okay, maybe I want to look at the best possible worst case. So maximize the minimum grade that I could possibly have. Or minimize the maximum grade that they could get, or something like this. In some cases, game theory does not tell you what to do because there's no single best answer. Maybe you want to say, okay, in the best case, maybe I'm going to choose beta because in the best case, I'm going to get a 1. So I'm only trying to get the best case. But if they choose alpha, then I get -3, sorry. So that might be like a high variance or like a risky sort of play. Versus this one, it's either a 0 or a -1. So you're like, okay, maybe that's a bit more, maybe you're more risk averse than someone else, so maybe you choose alpha, etc. But what if we are greedy and we know the other person is caring, for example, right? So what if it's no longer this symmetric type game where it's two of the same player? All right, what choice, will the choice be different if we know the strategy or the payoffs of the other person? So here we have the matrix for the greedy players. Here we have the matrix for the caring players. And what we're going to do is we're going to say, I'm greedy and they're caring, right? And then see what would happen. So we're going to take the first half from this matrix and the second half from that matrix, and now we're going to form this matrix. Okay. So as the greedy player, as the person over on the left, do we have a dominated strategy? Well, let's have a look. As the greedy player, is there a dominated strategy? Well, we do this algorithm. And if I'm doing this algorithm this many times, you're pretty sure that an example of this is going to be on an exam, right? So just keep that in mind. So is there a dominated strategy? Well, for the caring player, if they choose alpha, alpha gives me 0, beta gives me -1, so alpha is better. If they choose beta, alpha gives me 3, beta gives me 1. So yes, alpha dominates beta in this case. Now let's flip it around, and let's have the caring player on the left and C. Okay, so as the caring player in this case, what would you do? Well, let's have a look. What do we choose? Well, we look at the greedy player. Greedy player, fix alpha. So alpha is going to do better than beta. But look, if they choose beta, beta is going to do better than alpha. So nothing dominates anything else. So what might you do in this case? Hand up? Yeah. Okay, so we're resorting to that thing we said before of some other analysis of maybe minimums or maximums or averages or whatever. But there's one thing we haven't talked about yet. who are we playing against? We're playing against a greedy player. And we know that the greedy player, alpha dominates beta. So what's greedy going to play? They're going to play alpha. No matter what. There's no point in them trying to trick us because they'll just do worse. Right? So we kind of assume that we're playing against someone intelligent. But the greedy player, alpha, is always better than beta. So if we know greedy will choose alpha, right? So if they're going to choose alpha, then our best response to them choosing alpha is for us to choose alpha. So even if we don't have a dominated strategy or a strategy that dominates all the other strategies, it's possible in non-symmetric games, meaning we don't have the same payouts, to look at what they might do, right? And we probably do this in real life all the time. Like, if you're trying to predict what someone is going to do, or like, even if we're driving on the road, right? The best thing to do on the road is try and predict what that person ahead of you is going to do. You make a lot of decisions based on that. So if you're ever driving somewhere, driving fast or driving slow, the best thing to do is to drive predictably, right? Because, you know, if you got your right signal on and you're in front of somebody, they're going to make a decision based on that. And if you turn left, maybe they're like, oh, they're going right, so I'm going to go left, and then you crash into each other. So just behave predictably in ways that favor you. So someone could say, oh, what's the best thing that they would do for them? I'm going to base my decision based on that. And this is sort of the same thing. So put yourself in someone else's shoes. It's not just like an old phrase. It's actually something that you should do mathematically as well to see what they may do first. So this introduced the concept of a best response. What is a best response? So a best response is the strategy that performs the best against a given other strategy, right? If we fix the play of the other player, how do we respond to that? Well, ideally, we would pick the best thing that we could do. And if it's the best thing in response, then it's a best response. So in the previous example, we knew that the other player had a best choice, so we would choose our best response to it. And to know your enemy, you must become your enemy, Sun Tzu, right? So it's not necessarily your enemy, you know. To know the person you're playing with is to become the person you're playing with, whether or not you're cooperating or not. So what makes a game now? Let's try and define a game a little bit more mathematically. So we've only been really looking at the matrices, these matrices with like 2 players here, right? So it's kind of easy to define it in that, but these games could have any number of players. And if you have 100 players in the game, you may think, okay, what does that mean in terms of drawing this matrix, whatever. So, what makes a game? So there's some number of players, I, J, K, A, B, C, 1, 2, 3, whatever. There are some number of players in the game. And this game that I'm showing here, this is for the numbers game. So this is an example. So the players in that game was everybody in the room except for me. I just wasn't playing, right? So all of the students in the room were the players. Now, when it comes to a strategy in this case means a selection of a number, right? It means a choice of action, essentially. So lowercase sub I, that is a particular strategy of I. So lowercase sub I means the particular choice of you, or the particular choice of you, right? So someone wrote down 32, someone wrote down 71. That is lowercase sub I. Capital S sub I is the set of all strategies for each player, right? So for a particular player. So that would be 1 to 100. Everyone could have chose a number between 1 and 100. S is a strategy profile. A strategy profile is this. It's a particular selection from each player in the game. That is a strategy profile. S minus 1 is the choice for everybody except one person. Okay, so if I take out this person, then S minus 1 is, or S minus I, sorry, is the choice for everyone but player I. And the payoffs, U sub I of S, is the utility or the payoff of not only if I chose this number, but also factoring in everyone else's choices. So the utility for player I, given everyone chose all of this, because it always depends on what everyone chose. Some games might be a little bit like simpler, but in general, it depends on what everyone chose. Oh, and I think the first time I played this, I joked around that I was going to give $5 or something like that. And so we assume that these are all known values in these games, but this is how we would define a game in this case. So let's look at, we're going to keep going with more examples, because I'm just going to beat you over the head with examples until you understand. All right, here is another game where we have different choices. So before, each player had an alpha or a beta, each player had a split or a steal, but that is not necessarily the case. Here is a different game, okay? So we have player 1 and player 2. We have strategy sets, so those capital S sub 1, those are the possible strategy selections for player 1, which is T or B. And player 2, S2 is left L, C, or R. So I kind of look at this maybe as like a goalkeeper in soccer or something. One person chooses top or bottom, the other person left, center, or right. But, just trying to assign some values that make some sort of intuitive sense. And the payoffs are, well, the utility for player 1, if player 1 chooses T and player 2 chooses C, is, go over here, look, T, C, U1 is 11. U2 of BL, well, BL, U2 is the second one here, so that's 4. Okay, so that's the definition of this game here and its outcomes, etc. So let's ask some questions that might be on an exam about a game like this. Does player 1 have a dominated strategy? Okay, so in order to see if player 1 has a dominated strategy, we're going to look over everything that the other player could do. So player 2 chooses L, T is better, right? If player 2 chooses C, T is better. Or sorry, B was better for the first one, T is better for the second one, B is better for the third one. So one of them is not always worse than any of the others. So no, it doesn't have a dominated strategy. Does player 2 have a dominated strategy? So now we have to fix the other player, right? So let's look at fixing T, and then we look over all of the things for player 2. Well, choosing L would give -1, choosing C would give 3, choosing R would give 0. So in this case, C is the best. If we fix B, L would give us 4, C would give us 2, R would give us 0. So you may look at this and say, well, L is better for the second one, and C is better for the first one, so there's no dominated strategy. But that's what I warned about at the beginning. We're not asking, is one thing always the best? We're asking if one thing is always better than something else. What is a dominated strategy? And look at this. No matter what is chosen, T or B, C is going to give 3 or 2, and R is going to give 0 or 0. So yes, it does have a dominated strategy. C dominates R. And you're only able to see that now because I have more than 2 strategies on the screen, right? Because before, with only 2, if something is dominated, it means the other thing is always better. So it looks like we're asking if there's a best thing. But in this question, does it have a dominated strategy? Yes, it does, right? And it's because C always does better than R. And so the lesson we can learn from this is don't choose R. Why? Because C will always do better than it. And it doesn't mean that we should choose C. It just means that we would never choose R, right? So that's some of the logic in here. So, strictly dominated strategy. Now that we have these new definitions, how can we define that? So player I's strategy, S sub I prime, is strictly dominated by player I's strategy, S sub I, if the utility for player I of choosing S sub I, given that everyone else chose a particular thing, is greater than the utility for player I of choosing S sub I prime, given everyone else has chose that other thing, for all possible values of S minus I. So it says, no matter what anyone else chooses, is choosing one thing always better than choosing the other thing? And if it is, then that other thing is the thing that's dominated. But it does not mean, and we've seen this now, that thing that dominates that strategy is necessarily the best choice. We just know that we have a choice that we would never make. Okay, last game example for this class. You are a general defending an army, and I'm going to give the text description, then give a visual description. You have an army, and the attacker has 2 armies. Okay? There are 2 paths leading into your city, an easy path and a hard path. What that means will be obvious in a second. You can only defend one of these paths, so you have to make a choice of putting your army in the city at one of the gates. If the attacker chooses the hard path, they're going to lose 1. And if your armies meet, the attacker loses 1 army. And the enemy wants to maximize the number of armies in the city. So you want to minimize the number of armies in the city. So here's what this means. You have a city. You have your army within these gates. You're the general, right? So there's an easy path into the city. The army is just going to walk through the daffodils and get right up to your gate. There's also a hard path to the city. So the enemy starts with 2 armies. If they choose the hard path, it's just full of traps and bears and tigers and whatever, right? So they're going to lose one of their armies just by the fact that they chose the hard path. So if they choose the hard path, they lose 1. If they choose the easy path, they lose none. So you have to decide, where are you going to put your army? Right? And if you choose correctly and you meet the army, then you're going to destroy one of their armies. And so fewer get into your city, right? Please don't use this particular example for defending your hometown if that ever comes up, right? Just a game, but we'll show the utilities associated with that. So, what is the attacker payoff? The attacker payoff is going to be the number of armies that reach the city. That's how they can do the most damage. The defense payoff would be the number of attacking armies that you have destroyed. Does defense have a dominated strategy? Right? So, we are defending. We are over here. Our choices are easy or hard. That's where we place our armies. The attacker is here. The attacker has choices of easy or hard. So, do I have a slide on this or not? I'm not sure, but we're going to do the calculation anyway. So if the attacker chooses the easy path, then if we choose the easy path, we are going to meet them and destroy one of the armies, right? If the attacker chooses the easy path and we choose the hard path, we go to the other one, they just walk into the city. So we have destroyed 0 of them. So in this case, easy is better than hard. Okay. We look at the hard, if the enemy chose the hard path. If we choose easy, then the enemy loses one of the armies right away because they chose the hard path. They got eaten by tigers, right? So we don't destroy an additional one. If we choose the hard path, we meet them at the hard path, and both of their armies are destroyed. So that's kind of the best case scenario for us. So if they choose easy, then easy is better for us. If they choose hard, then hard is better for us. So there's nothing that's dominated in that situation. So let's have a look at the other one. Does the attacker have a dominated strategy? So this says, okay, I don't know what to do yet, right? Because I don't have a dominated strategy, so I can't see, there's nothing that's going to always be better. So put yourself in the shoes of the attacker, right? Listen to Sun Tzu. Does the attacker have a dominated strategy? Okay, so now we're going to fix these, right? So if the defense chose easy, if I choose easy, then I lose one of my armies at the gate, but one of my armies gets in. If the enemy chose easy and I chose hard, then yes, I still lose one of my armies over the mountains, but my army does get in. So it's tied. If the enemy chose easy, then I do the same amount of damage, no matter if I chose easy or hard. But if the enemy chose to defend hard, if I choose easy, I get both of my armies in. And if the enemy chose to defend hard and I choose hard, then I get none of my armies in. Right? So, if the enemy chooses hard, then choosing easy is going to do better. But if the enemy chose easy, they're going to be the same. So, in this case, easy weakly dominates hard, right? Because it will do at least as well in every case but it will do better in one case. So what would be the point, to choose the thing that will do worse in another situation? Now again, if you try and intuitively think about this, you may think about things like, oh, if we go over the hard route, where am I going here? If we go through the hard route, my soldiers would probably rather die in battle than die to elephants and giraffes in the mountains, or starvation, or whatever, right? So that is the thing that you would have to factor into your utility. But we are just saying the number of things. This is like a ruthless general, doesn't care about his troops, just cares about getting into the city, right? So in that case, we just make these very simplified, how many attackers reach the city type of things. And these sorts of calculations are used in real battle decisions. Battles, not only in real life where violence is employed, but in economics, right? You think about all the companies like Pepsi and Coke, that's a war. It's a different type of game, right? We are battling for the money of all of these different customers. And so things that are expressible in these type of games are, this type of game theory is often employed to make decisions in those situations. So then the definition of a weakly dominated strategy, well, before we said that strongly dominated meant that given everything that could possibly happen for everyone else, there's everything that we can do is better than another thing that we could do, right? That's not the same for weakly dominated. For weakly dominated, it's greater than or equal to for everything, but at least one thing is better. Okay, so that's the definition of weakly dominated. So you probably shouldn't play a weakly dominated strategy. If you know the attacker will take the easy road, then defend easy, right? So in this case, what we did was we said, what is the attacker going to do? Well, them choosing the easy weakly dominates them choosing the hard. Therefore, we should defend that. Because even if the attacker does the thing that's worse for them, you're still going to do as well because it's a weakly dominated strategy. So there's no trickery, there's no foolery or anything like that. So just as a quick recap, games have players, strategies, and payoffs. They also have outcomes, but the outcomes are what we translate into payoffs so that we can apply these algorithms to them. Players want to maximize their payoffs, always. Don't fall into the human intuitive trap of saying maybe or what if, because that was done at the step of translating outcomes into payoffs. Okay, so we always want to maximize our payoff, and maximizing your payoff could mean the minimization of your outcome, right? Like if you have kids, maybe you want their outcome to be better than yours, but you've translated that into utility. You've assigned a higher utility to that. And a strategy dominates another if it is always better, called strict domination, or as good, weak domination, as another one. Never choose to play a dominated strategy. Never, ever a strictly dominated, and probably never a weakly dominated one. And if there is no best strategy to play, consider the other player's best choices first. And if they have a dominated strategy, then you know they probably won't pick that one. So then you can narrow down the things that they are going to do. And if they do have a best choice, so if they do have a single strategy that dominates all other strategies, then pick the best response to that choice. Because there was no way they would choose another thing if it's worse for them. So some possible exam questions. Given a payoff matrix, compute the dominated or dominating strategies. And the dominating strategy would just mean this dominates that other particular one. I might explain why a given choice of strategy is good or bad for a particular matrix. Like, hey, I chose this. Why is that good or why is that bad? Compute the best response to a given strategy, or maybe construct a payoff matrix such that one given strategy dominates another strategy. And so that's it for this lecture. This lecture is always a bit short, but the next lecture is going to be using these concepts to build on that, and then that will give us nice, fun exam questions that we can do, and we'll play another couple games as well. So make sure you show up for the next one, because I want to get a bunch of samples, because we're going to compare the outcome of the numbers game in this class to that one, etc.